In this lecture entitled Size Matters Not, we're going to explore the various models of the atom. So the famous one that we have, size matters not, we have Yoda here, who shows that the size of something doesn't necessarily indicate its strength. So, famous quote by Albert Einstein says, "The unleashed power of the atom has changed everything save our modes of thinking, and thus we drift towards unparalleled catastrophe," referring to the atomic bomb. So, the goal for this particular presentation is number one, that you understand the experimental designs, results, and analysis that has led to the various models of the atom, and that you understand the current model of the atom and what we have not figured out yet. So, what we already know. We know that atoms consist of protons, neutrons, and electrons. We know that from chemistry. We also know that the experiments have led to a continual evolution of the atomic model. So, what we know about atoms has continually changed. In fact, this is the most common misconception about the atom. Okay, this is used by TV shows like The Big Bang Theory, or they're shown by a lot of different things to indicate what an atom is, but that's not our model of the atom. We should also know that the most current common model of the atom used in chemistry was the Bohr model. And although the Bohr model is a great model for the atom, it is not the most complete model at this point. Okay, what we learned in the lab. We learned that the discovery of the nucleus depended on Coulomb's law. Now, we actually talked about Coulomb's law earlier this year. And we said, okay, if we take positively charged particles and we fire them at the nucleus, then we see that these positive charges repel, or they deflect away. Because of that, we know that they repel away. We know that the nucleus must in fact be a positive charge. So the whole idea of the models of the atom has depended on some of the things that you have learned early this year. And this was actually called the Rutherford scattering experiment. Okay, actually it's really called the Geiger-Marsden experiment, but Rutherford was the one who developed the model based on it, so he gets a lot of the credit. Now, what else we learned in the lab? We learned that atoms consist of protons, neutrons, and electrons, and we learned that electrons can actually interact with these photons. So what you do is you fire electrons. If an electron hits just right, all of a sudden you see this cloud expand, or depending on what model you have, something will happen to the atom because of the interaction of the electrons and the photons. So, we have Dalton's experiment, and Dalton's experiment was the first one. This is kind of the review of chemistry. He said, hey, if I take different gases and I mix them together, what am I going to get? And he predicted, this is his prediction, that the gases would combine in different ways to form new products. So specifically, he said, okay, if I've got H2 and I've got O, I'm going to make H2O. And if I have H2 and O2, I'm going to make H2O2. And if I have H and I have O2, I'm going to make HO2. That was his prediction based on what he thought would happen. Now, whenever he did this, these were his results. He mixed hydrogen and oxygen and got water. But when he mixed three hydrogens with oxygen, he did make a water, but he had a leftover hydrogen. And you see this continual ratio right here. You see a 4, a 1. Well, he made a water, but then he had leftover gas. Or he had one hydrogen gas, he had two oxygens, and what he made is half as much water as he originally thought, and he had leftover oxygen. So you start to see a general pattern in the data, and what you see is you needed two hydrogens for every oxygen to make a water molecule. So you start to see these patterns in the data when you actually look at it. Now, this is what Dalton postulated based on the results of this experiment. He says that there are elements that are small particles called atoms. Now, this is really the first experimental evidence that we have for the atom. That's what makes this important. Before, the Greeks had thought of the idea of atomos, like, hey, eventually when I divide, I won't be able to divide anymore. But this is the first experimental evidence. It says that all atoms of an element are identical. Okay, so one hydrogen over here is the exact same as a hydrogen over here. He said that atoms cannot be created or destroyed. He said you can take atoms and you can rearrange them. So, in other words, you can take these two hydrogens and put them together to make H2, but you can't destroy an atom or create an atom. He also said that atoms can combine in whole number ratios to form new substances. And that's what we actually saw when you mix 2 parts of hydrogen with 1 part of oxygen, you got 1 part of H2O, or water. So he was the first one to kind of say, okay, these atoms can rearrange themselves. And so the final part is atoms can be combined, separated, or rearranged. So in other words, I can take 2 atoms that are stuck together and I can separate them apart. I can take 2 atoms that are separate and I can combine them together, or I can somehow rearrange those things. So these are Dalton's postulates. So this is our first atomic model that we have, and it was a basic model that is often referred to kind of as a marble model of the atom. It basically said that the atom is a solid, indivisible sphere, and that it can't be broken open, and that they are all slightly different. It's composed of elements. Now, that was a pretty good model for the atom, and it lasted for kind of a long time. But then we get to this idea of the Thomson experiment. Remember, all scientific theories are open to revision. So whenever you have an experiment that contradicts the previous model, you have to adjust the model accordingly. So if you were to take a look here, we have the Thomson experiment. And it says that a cathode ray can be produced by subjecting a gas to a large voltage. So I have this large voltage that's right here, and what happens is I produce a cathode ray. And I can take these cathode rays and I can fire them between 2 charged plates. It turns out that when I do that, I know that opposites attract. So by doing this, I'm trying to see, if I take this thing, will this particle deflect one way or the other? Because based on Coulomb's law, if this particle right here has some sort of charge, it will deflect either up or down based on what this charge is. If it's positive, it'll deflect downward. If it's negative, it'll deflect upward. So this was the Thomson experiment. This is what he saw. He said that whenever the charge so this is unknown. He didn't know what the cathode ray charge was, but he did see that whenever the top plate was positive, it would deflect upward. Okay? He also saw that if you had both plates as positive, nothing happened. And if you had one negative and one positive, so what you saw is you always saw it move towards the positive plate. And it's interesting because you know that if it's always moving towards the positive plate, that it must be negative. And it turns out that the results of this were that Thomson found the electron. His analysis was that atoms can be divided into smaller constituents. This directly took out Dalton. Dalton was no longer the man at this point because a key component of Dalton's postulates was that the atoms can no longer be divided. Thomson says, no, 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 no. Atoms can be divided. Now, the second one says that atoms are electrically neutral, but have negatively charged particles called electrons. So the fact that he had this negative charge indicated that there had to be a negative charge. But the overall atom was neutral. So if you have an overall neutral atom, and if you have a negative charge, that implies that there must be some sort of positive charge here. Now, Thomson didn't have any luck in actually finding this positive charge, so he developed his own model of the atom that sometimes is called the chocolate chip cookie model or the plum pudding model if you're British. But basically what it says is that you have a diffused positive charge. So the entire atom consists of positive charge, with the exception of these little nuggets right here, and those little nuggets are the negative charge. So if you are not in a negatively charged particle, you're positive. Okay, this was the Thomson model of the atom. Now, the Geiger-Marsden experiment came up, and sometimes it's referred to as the Rutherford experiment. Geiger-Marsden are actually the people who did it. They were graduate students of Rutherford at the time, and Rutherford used their data appropriately to develop a model. But we want to make sure we give credit to everybody at this point. So this is the experiment that they set up. They said, okay, we have alpha particles that are helium atoms. So an alpha particle is a helium nucleus. So basically what it is it consists of 2 protons and 2 neutrons. Because of that, this entire thing is positively charged because there are no electrons that are associated with it. So now I took this and I fired it at gold foil, just a few very, very thin layer of gold foil. Now, gold is still a solid, so the argument was that if you take these positively charged particles and you fire them very, very quickly, most of them would pass right through the gold foil. This was designed as the equivalent of taking a loaded gun and putting a tissue paper at the end of it and firing the gun at the tissue paper. Now you would expect it to go through the entire way. But what they did is they surrounded the entire gold foil with a detector. And this detector would notice whenever a alpha particle struck it. So they would have a map showing where all these deflections occurred. So these are the results. They did 8,000 trials. When they did 8,000 trials, they had one particle with a deflection that was this large deflection. The vast majority of the particles went straight through. Okay, but occasionally you would see some deflect at small angles. So they would deflect like this. And that was weird. They expected it to go straight through. If it's like firing a bullet through tissue paper, the tissue paper can't deflect the bullet. So this was kind of an interesting question. They said, okay, well, what deflected it and what happened here? How could you actually take this thing, fire it at this thing, and have it bounce straight back? That was really not what they were expecting to see. So they checked it to make sure there was no error. There was no error. So they said, okay, that means that there is a positive charge somewhere in the atom. In fact, they said that it was at the center. Okay, they said there's a small positive charge. Now remember, this says, hey Thomson, you're not right anymore. What you did was good, but your model is no longer correct. There is not diffuse positive charge. If Thomson's model was correct, what you would see is every one of these positive charges that came in would deflect, because positive charges would repel positive charges. But most of them went straight through. Because most of them went straight through, you can say that the vast majority of an atom is consistent of empty space, something in which another nucleus can pass right through another atom. Now, occasionally, you would see there would be a deflection, a large deflection, or a small deflection. That means that one of the particles that you fired at the atom came very, very close to the nucleus. And the fact that it turned around and came back, as opposed to attracting to it, indicated that this thing was interacting with a positive charge. Now they took this positive charge and they named it the nucleus. Now sometimes this Rutherford model is referred to as the planetary model. And this is still the one that most people think of when they think of the atom. They think, okay, here's this stuff in the center, and now I've got these things going in orbits around it, and there's my atom. Okay, this is no longer the correct model of the atom, but it's the one that stays with people the most because it's the easiest one to kind of visualize and comprehend. People say, oh, well, it's like the planets going around the sun. And it is similar in this case, but we'll find out that that's not exactly what happens. The basics of the Rutherford model says that you have a positive nucleus at the center of the atom. You have electrons that are moving around the nucleus at a variety of distances, just like planets. So here you have Mercury, you have Venus, you have Earth, you have Mars. They're all traveling in a circle around this, and they're primarily attracted by positive and negative charge interactions, so you have Coulomb's law. So this was the Rutherford model. And the Rutherford model was a pretty good approximation, but once again, we have another experiment that can, shed a little bit of doubt on. And this was the Bohr experiment. The Bohr experiment said, okay, what we're going to do is we're going to take these glass tubes and we're going to fill them with gases like helium or argon or anything that they had available to them at this point. And then what they did is they subjected these gases to very large voltages. So you had an extremely large voltage at this point that you connected it to. And that voltage actually provided energy to the gas, and so it excited these gas molecules to a very high state. Well, the gas molecules don't want to be at this higher energy state, so what we learned in chemistry is that the electron would fall back down. And in doing so, it emitted a particle of light known as a photon. So when that particle of light known as a photon was emitted, you started to see, okay, well, what kind of patterns for photons would we get? Remember, we had the Rutherford model of the atom that said you could have electrons at any distance. They could be any distance away from the nucleus. Well, if you look at this, Bohr found this idea that there are certain patterns that people see. Helium, hydrogen, mercury, neon. each element gave a unique spectral pattern. Every atom gave a unique one. But it didn't matter what type of helium it was. No matter what he did when he put helium in there, this is the pattern that he got. No matter what he did when he put hydrogen in there, this is what he got. In fact, when he put hydrogen and helium together, you got a combination of these two. So you'd have these lines match up where you'd have multiple lines on the same thing. These would line up with these. Okay, so it was interesting because each element gave a unique pattern and it always gave a consistent pattern. And it also gave very specific values. Okay, it didn't have this broad range of numbers. So, what patterns do you see in the data? Well, let's take a look at it. Every atom produces a consistent and unique spectral pattern. Most elements have very, very few colors. Now remember, in the other model, the Rutherford model of the atom, an electron can be any distance away. So because of that, it could have any energy. If it had any energy falling from here to here, if this were true, all atoms would produce all colors. That didn't happen. Instead, what you see is you see very specific patterns. So because of that, what we say is we say that that can't be correct. Instead, we say electrons must have discrete or certain energies. They can't have all energies. They have to have just a couple of small different values. And this is where we get the Bohr model of the atom. It's very similar to the Rutherford model of the atom. It says that you still have this positive nucleus, and in that positive nucleus, you have electrons that surround that nucleus. Okay, that's not different. So this is very, very similar to the Rutherford one. The difference is it says that the electrons must travel at a specific distance. So it can be here or it can be here, but it cannot be in between. And Bohr actually called these things orbitals. And you probably talked about orbitals in chemistry. So whenever you add energy to an atom by heating it up or hitting it with light, it actually causes an electron to move from one orbital to the next orbital. Whenever an electron moves from one orbital to the lower orbital, it actually produces a photon of light. Because these are set distances between the two, falling from here to here will always produce the same color of light. So that is the primary difference. Not that there were electrons, not that there were protons or neutrons. It was the fact that the electrons had to be in specific locations. Okay, it didn't always have to be at this exact. It had to be somewhere at that distance. Now, then we have the Chadwick experiment. The Chadwick experiment was the way in which we found the neutron. Okay, it says it right here, just so you know. What it did is it took a radioactive element called polonium, which gives off alpha particles. Yes, it is the same alpha particles that we saw earlier in the Geiger-Marsden experiment. And what happens is when you collide these alpha particles with a beryllium sheet, okay, particles appear to come off the beryllium. So the beryllium loses mass. Now, then it collides with this paraffin. And when it collides with the paraffin, you'll see that the beryllium lost mass, particles collided with the paraffin wax, and that these particles were attracted to a negatively charged plate. So what you see is that neutrons came off the beryllium. That's the reason why. The reason why I would know it was neutrons is if you put a positive plate here and a negative plate here, nothing happens. There's no attraction or repulsion one way or the other. So we know that these are electrically neutral at this point. Then it hits the paraffin wax. And after it hits the paraffin wax, you will see that it is accelerated towards a negative plate. So what happens is the neutron is somehow converted into a proton, which means that there has to be an electrically neutral particle in an atom that they've called a neutron. And a neutron consists of a proton and an electron. It's a little bit more complicated than that when you look at it, but it basically consists of a proton and an electron that are kind of combined. So his analysis was there's an electrically neutral particle. The particle has a mass similar to a proton. The particle is capable of being converted into a proton, and it has to reside in the nucleus with the proton. So basically he kind of rounded out our idea of the nucleus, that we have protons and neutrons and electrons. Now, the current atomic model that we have is something called the Schrödinger model, or more commonly known as the quantum mechanical model or the wave mechanical model of the atom. And basically, the primary idea behind the Schrödinger model of the atom is that you can't say that the electron is here or here or here or here, but instead you have to look at it in terms of probabilities. Okay? So the electron location can't be said with certainty. Now you may be thinking, well, in chemistry, I learned that the electron is in one of these orbitals. It's like in a p orbital, or it's in an s orbital, or something like that. That is a good approximation of for what actually occurs. And you can actually see the s orbital right here. It is not a solid sphere as it's represented in chemistry. Instead, it's kind of like the sun. There's a really bright spot and it kind of dims out as you go here. This represents the probability of finding an electron. So whenever they draw that sphere and say the electron is here, it's not entirely inaccurate. It is a 90% probability that the electron is there. When you look at these things right here and you see those dumbbell shapes, okay, it's not that the electron is not there, it's there is a 90% probability that it is there. And it's that way for every shape. Now, the new thing about these quantum mechanical models is you have these things called nodes. And those nodes right there are places where there is zero probability of finding an electron. And if you look, the shape of these starts to very much resemble what we had for the Bohr model of the atom. If you look, the electron can be here or it can be here, but it can't be in between. So you start to look at this idea of the fact that the electron has a probable location. It matches up very well with the Bohr model of the atom. In fact, it simplifies very well to the Bohr model of the atom. So, the equations, being able to predict the location of an electron is very, very, very difficult. This is the kind of math that you would see when you were trying to predict the location of an electron or the probability of finding an electron. Not only would you have this, but you would have to do something called integrate, which is calculus, 3 times, and then you would have to take this function and square it. So this whole thing would have to be squared, or this whole thing. It gets extremely complicated. The math is well beyond anything that's expected of you in high school, and for the most part, even undergraduate. But you should be able to say, okay, there is math that allows me to get a general idea of the prediction of a location, or the prediction for the location of an electron. Okay, now whenever you start to look at any atom that is more than one electron, that is beyond our ability, even our fastest computers, to figure out and solve. So, explain how our model of the atom would be different if the results of the Geiger-Marsden experiment would have resulted in the following. If we had zero deflections, okay, zero deflections at all, at this point you would say, okay, if something, and I'm firing a positive charge at it, goes straight through and there are no deflections, there are two possible conclusions. The first one is that there is no positive charge. Okay, now remember, Thomson had assumed there was a positive charge because there was a negative charge and atoms appeared to be neutral. Okay, the second possible conclusion in this particular case would be that the nucleus was very, 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 very small. Okay, in fact, so small that it couldn't interact with this particular whatever we were firing at. So those are the two possible conclusions if the results had been different. It's called hypothetical deductive reasoning. The next one says, assume that electrons can have any energy in the atom, describe what the Bohr line spectra experiment would have been, and then justify using the clear method. Now we've kind of talked about this already, but if you have a positive charge there, and the electron can be any location, so the electron can fall from here to here to here to here to here, basically you can produce any color of light. Well, if you can produce any color of light, instead of having a nice clean spectra where you have lines here, you would instead have all colors of light produced. Okay, so using the clear method, you would say all colors are produced. Okay, all colors are produced. The evidence that you have to support that is that you can produce any color of light if you have the right distance that the electron falls. So if the electron moves from this energy to this energy, you can produce this color of light. Your reasoning that you have for producing all colors is that the Rutherford model did not put a location for the electron. So because of that, the electron can be at any location and therefore can move from that location to any other location. At that point, you can produce all colors of the spectrum, and we know that's not the case, but this is once again one of those examples of hypothetical deductive reasoning. The last example we have says, which of the former is the most precise model of the atom? And the answer is the quantum mechanical model. And the reason why is because it expands on every other model. And people say, oh, well, the Dalton model of the atom was wrong. And it's not. If you look at the Dalton model of the atom from a certain point of view, it appears to work. But when we look more specific, now we have an experiment that shows something different. And the Thomson model appears to work until we found an experiment that looks at it in a more specific light. So it's not that the other ones were wrong, there were just specific aspects of them that it didn't address. But the quantum mechanical model that we have is the one that is the most precise because it takes Dalton, it takes Thomson, it takes Rutherford, it takes Bohr. All the best of all these things go into the quantum mechanical model. Now that we know about the idea of quantum mechanics, we can now go ahead and say, we can explore the idea of what can we do with this new idea of quantum mechanics. Now, what we need to do is we need to rehash some of the things that we've talked about earlier this year. Earlier this year, we talked about the idea that energy is equal to Planck's constant times the frequency. And we also said that C equals lambda F. And you can combine those two into this formula right here, where you have energy is equal to hc, which are both constants, divided by lambda. So that's a really important concept. Now we can say, okay, I also had an expression that said energy is equal to 1/2 mv squared. Specifically, this is a kinetic energy equation. Now, if you were to take a look at this, you have the idea that 1/2 mv squared. Well, if you were to take the m and the v and kind of write it out like that instead of mv squared, you can rearrange this thing. And what you can do is you can say v and m, and that right there represents the momentum. So what I'm doing is I'm getting rid of the m and the v, and I'm going to replace it with p, which stands for momentum. So the kinetic energy equation becomes 1/2 p v. Well, now, if we realize that this is light, remember we're revisiting the idea of light, this turns into the term c, which is where you get the term 1/2 pc. Now remember, this is an energy equation, so I can turn and I can set the other half equal to my other energy equation, which is where this comes from. Now if you see this, I've actually already canceled out the c right here because you have c on both sides. So because of that, you can cancel it out on both sides. And now what you can do is you can rearrange this equation for wavelength. And when you do that, you end up with the expression wavelength is equal to 2h divided by p. Which is really interesting because you have this idea that whenever you increase the frequency, you increase the energy, right? And we kind of see that as well. And when you increase whenever the wavelength goes down, you've got this uncertainty in a position that's going to increase. So you've got this idea that whenever this momentum term goes up, this wavelength term is going to go down. So it's an interesting contrast. More often than not, you'll see it in terms of this. You will take this thing right here and you will say wavelength times p is equal to 2h. And what you're saying is that the wavelength for a particular item and the momentum of that particular item has to equal 2 times this constant. And that's the idea of what we call the Heisenberg uncertainty principle. It basically says that you can only know certain amounts of information. The Heisenberg uncertainty principle says that the momentum and the position of a particle cannot be known exactly. Instead, what you have is you have uncertainty in these two things. It says the more that you know about one, the less you know about the other. So if I know everything that I need to know about momentum, then I know nothing about position. Okay, if I know everything that I need to know about position, then I know nothing about momentum. And you can see this at home with Heisenberg, and I says I can't find my keys. In other words, he's saying that I have no idea what the position is. Okay, if you have no idea what the position is, you probably know too much about their momentum. It's a joke as far as that's concerned. So now, if we move on. Now, the Heisenberg uncertainty principle says that the uncertainty in position and the uncertainty in momentum have a maximum possible value. So in other words, you have to have at least some uncertainty. It's got to be greater than this h bar over 2 number. Now, h bar over 2 is really just a fancy way of saying h divided by 4 pi. The term h bar is used because h over 2 pi is used a great deal in quantum mechanics. Now, we're not really going to deal with that. You just need to know that h bar over 2 is equal to h over 4 pi, where this h term is 6.626 times 10 to the negative 34th. It's still that Planck's constant number. Now, everything else that we're going to use in this thing is we're going to talk about momentum. Okay, we're also going to talk about position, but we've talked about that quite a bit. You also have this idea of momentum and mass. These mass and velocity can combine to make momentum. So everything is the same. We've talked about position, we've talked about momentum, we've talked about mass, we've talked about velocity. Really, the only thing that's new here is this idea, this h over 4 pi. Basically, what this is saying is that there is a minimum value of uncertainty. So, when we take a look at it, we first have this idea of us trying to design an experiment. And if you're trying to design an experiment, you have this idea of how are we going to do it. Really, the easiest experiment to comprehend is the idea of trying to find the position of an electron. Now, we already said that the electron is basically, there's no way of knowing exactly where it is. It exhibits what we call wave-like behavior, which means that it can travel anywhere in relation to the proton. Now, there's a probability of finding it in a certain place, but it's very difficult for you to find its exact location. So, if you are trying to find its exact location, the easiest thing to do is to take a very large object, say another atom or say something very large, and put it in the path of an electron. In other words, where it's most likely to collide. And then what you can do is you can measure the energy drop as the electron collides with that with that object, whatever it is. Whenever the electron collides with that object, what I can say is the electron is right there. Because it's made this collision, it's attached to this particular object, so I know at the point of collision that the electron is right there. Unfortunately, as a result of that, I have no idea how fast it was going when it struck the object. I have no idea of how much mass it had to begin with. And a lot of people will say, well, couldn't you just use the idea of conservation of momentum? The idea that you have this very small electron, and how much does it affect this? And it turns out that's a really good idea, but it doesn't quite work that way. And then you have the idea of energy is related to momentum, and there are some really tricky things when you get down to this level, this idea of quantum mechanics. You have to deal with probabilities and things like that. So, really, the basic idea of it is if you were to collide this thing, you have no idea how fast or what its mass was as it makes that collision. So next, we have this whole idea of you have an electron moves at 2 times 10 to the 7th meters per second. And we want to know what the uncertainty is in position is. Now we have the Heisenberg uncertainty principle, which is delta x or times delta p has got to be greater than or equal to h bar over 2, which remember we said is h over 4 pi. Now, this 2 times 10 to the 7th term, that right there represents our velocity. What we are trying to solve for is the uncertainty in position, this delta x number. So we also need to know the mass, and the mass is the same for an electron. We're going to assume it's the classical mass of an electron, which is 9.11 times 10 to the negative 31st kilograms. So what we want to do is we want to go ahead and solve for this particular value. So how we're going to do that is we're going to say delta x, because we still don't know what that is, and then we're going to have 9.11 times 10 to the negative 31st times 2 times 10 to the 7th, and that right there represents, those two together represent the momentum of the object, the mass times its velocity, has to be greater than or equal to h, which remember my h term is 6.626 times 10 to the negative 34th, divided by 4 pi. Now it is really important that when you do this, you need to make sure that you treat that 4 pi in parentheses. So really what you need to do is you need to take these values right here that are on the one side, and we're trying to isolate for x. So because of that, we're going to divide both sides by this 9.11 times 10 to the negative 31st, 2 times 10 to the 7th number. So I can actually write it, and I'll make sure we put it different colors so we can see what it is. 9.11 times 10 to the negative 31st, and then you have 2 times 10 to the 7th. When you take those quantities and you divide them by both sides, and it's 2 times 10 to the 7th. When you multiply those, these will cancel out. And whenever these terms cancel out, what I'm left with on one side is delta x. And then I have the greater than or equal to sign. and then I can actually plug this into my calculator. Now you need to be very, very careful when you plug this into your calculator. And you should expect a reasonably small number. And whenever you get this, if you multiply it out correctly, you should get the number 2.89 times 10 to the minus 12th meters. So our uncertainty in the position of an electron is small. It's 2.89 times 10 to the minus 12th. But on the scale of an electron, that is a pretty big number. So the more certain I am about its particular velocity or its momentum, the less certain I can be about its position. So as this number becomes more and more likely, this number right here becomes less and less known. Okay, now it says police use radar to accurately determine the velocity of an automobile. It says an enraged motorist argues that radar guns are so accurate in determining velocity that the operator cannot be sure of the position of the car, so it may in fact have measured the velocity of another car. He cites Heisenberg's uncertainty principle. Now, this is a common idea that, okay, well, I can use Heisenberg's uncertainty principle to get out of something or other. So you have the idea that the uncertainty in position times the uncertainty in momentum is equal to, or is greater than or equal to, h bar over 2. Okay, that's the statement of Heisenberg's uncertainty principle. So this number right here is going to be a very, very, very small number. Okay, whenever you take it and multiply it out, it's 6.626 times 10 to the negative 34th divided by, and since it's divided by a very large number, and that very large number, well, it's actually divided by 4 pi, but that makes it a very, very, very small number. Okay, so you're something times 10 to the minus 35th. Okay, maybe it's the minus 36, but it's a really small number. Now, generally, the reason why this gets to be a bigger number, the uncertainty in position or the uncertainty in velocity, is because this momentum term on the one side. The momentum term is generally small because you're talking about the mass of an electron, which is very, very, very small. But because you have the mass of a car being very large and the velocity being pretty small, okay, this term actually ends up having almost no effect on this. So whenever you look at it in terms of large scale everyday things, the uncertainty in position, the uncertainty in velocities end up being so small that they make no real difference. Quantum mechanics works for electrons, photons of light, to some degree a nucleus. But even a nucleus is large enough where quantum mechanics starts to give way to you can just use classical mechanics. So really, quantum mechanics, when we're talking about this thing, we're talking about electrons and smaller. Now, it's really important when we're dealing with electrons and electricity and things like that, but really, it's things that are very, 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 very tiny. It doesn't stop with quantum mechanics. There has been a lot of advances. Now, quantum mechanics is generally where most physics classes will stop, and we are going to talk very briefly and very conceptually about some of the stuff that's happened. What you see here is you see the number of particles that have been found. These are the number of particles that have been found since, the turn of the century, or the 1900s. And if you look, you see an explosion of particles that were found. I mean, right here, you had the electron. The electron was found just before 1900. And then you have the idea of the proton finally being isolated before 1920. Here's the neutron. Those make up the basic parts of the Bohr atom. But now you have the idea of a positron now. And then you talk about muons, and you talk about quarks and up quarks and down quarks and bosons. And if you look at this, since 1950, look at the number of subatomic particles that have been found. It's just an astronomical number. Okay, we know a lot more about the atomic theory than we did at the advent of quantum mechanics, which is right in this area right here. This is an idea of quantum field theory. Quantum field theory is a highly mathematical concept. Okay, it is almost impossible to explain in terms of a conceptual basis, other than the fact that what it does is it takes quantum mechanics and the idea of relativity and puts them together. Now, we haven't talked a lot about relativity. That's actually in the next lecture. But the two ideas were initially thought to be completely separate, but they were kind of put together with this idea of quantum field theory. And basically the gist is a force has to be carried by something. Okay, if you push something, there's got to be something that makes those particles interact. And what quantum field theory was says that a force being exerted on another is an exchange of subatomic particles. So, for example, you have object A and you have object B, and the reason why they exert a force on one another is because they exchange tiny subatomic particles. And by subatomic particles, I'm not talking about protons, neutrons, and electrons. I'm talking about things that are smaller than that make up protons, neutrons, and electrons. Okay, so we're talking about extremely small things. Now, the idea of quantum field theory generally won't come up to you unless you take a senior level or sometimes even a graduate level physics course. But it is important to understand that you do need to know what it did, that it linked quantum mechanics and relativity. In addition to that, we have this idea of quantum electrodynamics. And basically, what it did was it took Maxwell's equations. Okay, Maxwell had four basic equations that explained electricity and magnetism. And what he did is this linked quantum mechanics and this idea of electromagnetism. It explained in terms of the atom how these equations worked. And one of the most famous people that did this was this guy right here. His name is Richard Feynman. And Richard Feynman was a famous physicist. He was the youngest physicist to work on the Manhattan Project and help build the first atomic bombs. He was a professor in California for a long time. He came up with this idea of quantum electrodynamics. He was actually the first person to invest, or he was the lead investigator whenever the first space shuttle exploded in 1986. He's a very interesting guy. I would highly recommend that you listen or you download his book and you look at his book or you download some of his lectures that are available on the internet. It's really great especially if you look at it. There's a book called Surely You're Joking, Mr. Feynman. It's a really, really interesting spin on how to do some of these very complicated physics problems. Then you have this idea of quantum chromodynamics. Quantum chromodynamics was the idea that you could link the strong nuclear interactions at the quantum level. So if you look, we're slowly adding the different pieces that we know. We're adding electromagnetism, we're adding the strong nuclear force, and it basically brought up these ideas of these elementary particles. Okay, the idea of quarks and leptons and what are the force carriers and those sorts of things. But now we needed to link all these together, and that was done with what we call the Standard Model. The Standard Model united quantum mechanics, quantum field theory, quantum electrodynamics, quantum chromodynamics, and it had this idea of we're getting to the idea of a theory of everything. Now, this theory of everything we still haven't gotten, and the reason why is gravity. Gravity was the first force we had any understanding of. Newton did it in the 1600s. But it's the only one that we can't explain in terms of quantum mechanics. Now, this is the one that they're really trying very, very hard to figure out at CERN. CERN is a large particle accelerator that you see right here. They're working very diligently, and in fact, there is evidence that they have found what is called the Higgs boson. And the Higgs boson is the particle that imparts mass. And if they did that, that's a giant step forward in trying to explain a quantum theory of gravity. So it is interesting that although gravity was the first that we know about, it is the only one that we haven't united with quantum mechanics. So you have this whole idea of this is the Standard Model. So you have bosons, hadrons, and fermions, and they kind of overlap a little bit, and then the idea of quarks, and then you've got photons and Higgs and mesons and neutrons, and there's a whole family of subatomic particles that are smaller than what you've ever heard of before. So you see baryons or protons, neutrons, and electrons, but several of you may not have heard of the neutrino or kaons or pions, or there's lots of different particles that you haven't heard of. Now, one theory of everything is the idea of string theory. Now, string theory is a popular theory that you hear about on a lot of things like the Discovery Channel. Now, one of the biggest problems with string theory is it is an attempt to unite everything. What it says is that every particle that you see, all those lists of particles, neutrions and pions and all that, are really vibrating strands of energy. So you have energy that vibrates, and whenever it vibrates a certain way, that's what makes up a proton. And this one over here looks different, and because of that, that makes this an electron. Now, one of the problems with string theory is that it's currently untestable. Not only that, but there is not even a mechanism to say when we can do this, then we can test string theory. Okay, it's one of those things that it borders on the line between science and philosophy. And the reason is science depends on the idea of a testable hypothesis, whereas string theory doesn't have a testable hypothesis. And you see that kind of summed up here. It said, I just had an awesome idea. Suppose all matter and energy is made of vibrating strings. Okay, what would that imply? I don't know. And that's the whole idea. It doesn't mean anything at this point because you're just saying, well, maybe it is, maybe it isn't. We'll never know. And so some people question whether that's science or not. It's an interesting thing for you to test about because it brings up the whole idea of science that we talked about at the beginning of the year and look at where we are now.